friends, welcome to this lecture. In this lecture we will discuss the Lyapunov stability of dynamical system. In fact, we have already discussed some concept of stability in previous few lectures also, but in this lecture in all those lectures when we try to discuss the say stability of linear system, then it is a problem of finding the say sign of real part of the eigenvalues of the linear matrix A. But when we try to solve the when we try to find out the stability of nonlinear system, then we consider the corresponding linear system and then we try to find out the this similar thing which we have solved, which we have done for linear system. So, in all those cases we basically try to find out some solution and then we do all this thing. But in case of Lyapunov stability, we need not to find out solutions of the dynamical system. In fact, here we try to find out a function which is known as Lyapunov function having certain properties. So, here without solving, without finding the solution of dynamical system, we can find out the stability behavior of the dynamical system. In fact, one more thing which we can obtain through the Lyapunov stability or with the help of Lyapunov function, that here we can find out the reason in which your dynamical system is stable, unstable or say asymptotically stable thing. So, here the new thing is that we can find out the reason in which your solution is stable here. So, these things we can obtain with the help of Lyapunov function, but the difficult part in case of Lyapunov function is to construct the Lyapunov function. So, if you are good enough to find out the Lyapunov functions, then we can achieve all these benefit here. So, in fact, there is no general method to find out the Lyapunov function for given dynamical system. So, all these things we try to discuss in this and the next lecture. So, let us first start the Lyapunov stability of a nonlinear system. So, first consider an autonomous system x dash equal to f of x. Here f is a continuous function from Rn to Rn. So, it is a basically n cross 1 system, x is a n cross 1 vector, and assume that f is smooth enough to ensure the existence and uniqueness of the solutions of one. So, it means that here we are assuming that dynamical system is having solutions and solutions are satisfying the uniqueness conditions also. So, let omega be an open set in Rn containing the origin here. So, now the function Lyapunov function V which we are talking about, it satisfies certain properties. Let us do some basic concept and try to identify those properties. So, first let us define certain things. So, suppose Vx is a scalar continuous function defined in a omega. So, omega is already defined, omega is an open set in Rn which contains the origin. So, V is a scalar continuous function defined on omega. Then we call a scalar function Vx is said to be a positive definite on the set omega if and only if V of 0 is 0, it means that at origin it is 0 and in all other point it is positive. So, Vx is positive for all x which are non-zero and x belongs to omega. So, it means that positive definite means that it can it is taking value at origin and in all other point it is taking only the positive value. So, in this case we say that Vx is a positive definite on the set omega where it satisfies these properties. Now, second, a scalar function Vx is said to be positive semi definite on the set omega when V has the positive sign throughout omega except at certain points where it is 0. So, it means that positive semi definite means it is taking only the non negative values. So, it is taking either the value 0 or the positive value, right. So, it means that there are certain points where it is 0, in all other points it is taking only the positive value. So, in that case we say that Vx is a positive semi definite on the set omega. Similarly, we can define the negative definite. So, a scalar function Vx is negative definite or negative semi definite on the set omega if and only if minus Vx is positive definite. So, it means that Vx is negative definite means that minus Vx is positive definite. So, here we simply say Vx is negative definite means minus of Vx is positive definite. Similarly, Vx is negative semi definite means minus of Vx is positive semi definite here on the set omega. So, so here Vx is positive definite, then minus of Vx is negative semi Vx is positive definite, then minus of Vx is negative definite, and if Vx is positive semi definite, then minus of Vx is negative semi definite here. So, in this way we can define the positive definite, positive semi definite, negative definite and negative semi definite. So, let us take some example to identify this. So, first let us say for n equal to 3, now consider some functions. So, here first function is v1x equal to x1 square plus x2 square plus x3 square. So, since it is sum of squares, so it will always take the value 0 or say positive values. So, if you look at when it will take the value 0, so v1 x is equal to 0 implies that x1 square plus x2 square plus x3 square equal to 0. So, it means that this is possible only when x1 and x2 and x3 are all 0. So, it means that it is taking value only 0 only on the only at the origin, and in all other point this is basically positive value, it is sum of positive value. So, it is taking the positive value. So, it means that it is taking 0 value only at the origin, and in all other point where x is non-zero it is taking the positive value. So, v1x is your positive definite scalar function. Now, similarly we can define v2x equal to x2 square. Now, here again we can say that since it is v2x is given as a square of some x2. So, it means that v2x will take only say non-negative value, and if you look at, if you put v2x equal to 0, then this implies that your x2 square equal to 0. So, this implies that x2 equal to 0, but it gives no condition on the other component x1 and x3. So, it means that v2 x will be 0 provided we have all this kind of structure here. So, x1 x2 x1 0 x3. So, it means that on x1 x3 plane where x2 is equal to 0, v2x may take the 0 value. So, it means that it is taking positive value, non-negative value throughout the domain, and it is taking 0 value other than origin also. So, in this case v2x is a positive semi definite function. So, here it is PD positive definite, it is positive semi definite here. So, it is taking only the negative non-negative value here. So, and it is taking value 0 other than origin also. So, it is positive semi definite function. Now, define v3x equal to x1 square plus x2 plus x3 whole square. Again it is given as sum of squares function. So, it is basically taking non-negative values. Now, we need to find out that at what point it is taking the value 0. So, here it is taking the value 0 provided that x1 equal to 0 and x2 plus x3 is equal to 0 here. So, here this may gives you the entire plane. So, we can say that x2 is equal to minus x3. So, it may take value other than origin. So, it means that here it is taking non-negative value and it may take value 0 other than origin also. So, in this case your v3 function is again a positive semi definite function. Similarly, we can define one more function, say v4x as x1 is square plus x2 is square minus x1 4 minus x2 4. Here let us take n equal to 2 here. So, it means that we have only x as x1 and x2 here, right. So, if we look at this V4 x square, now it is quite difficult to find out whether it is taking all the positive value or negative value. So, here if you look at this x1 square plus x2 square, I can write this as norm of x whole square minus x1 to power 4 minus x2 power 4 here. Now, here we know that norm of x square is basically x1 square plus x2 square. Now, what about this x1 to power 4 plus x2 power 4? If we add, so this I can write it as x1 square plus x2 square whole square of this minus 2 x1 square and x2 square, right. So, minus of this will be, so I can write this as, this is what, this is norm of x to power 4 minus 2 of x1 square minus x2 square, this minus x1 square x2 square. So, here there is no minus, okay. So, this implies this. So, here if you look at x1 to power 4 plus x2 power 4 is some values which is less than x to power 4 here. So, I can write that x1 to power 4, x1 to power 4 plus x2 power 4 is something which is less than is greater than or equal to, sorry, this is x to power 4 here. So, it means that here we are subtracting some positive value, some non-negative value to get x1 to power 4 plus x2 to power 4. So, it means that x1 to power 4 plus x2 to power 4 is less than norm of x to power 4. So, minus of x1 to power 4 minus x2 to power 4 is greater than or equal to norm of x to power 4 here. So, I can write this as this is greater than or equal to. So, here we can say that x1 to power 4 plus x to power 4 is written as norm of x to power 4 minus 2 x1 square x2 square. So, if you use the value x1 to power 4 plus x to power 4 as this, then we can write V4x as norm of x square minus, in place of x1 to power 4 minus x2 to power 4, we are writing minus x to power norm of x to power 4 plus 2 x1 square x2 square. So, we can let us use this here. So, V4x we have written as norm of x square minus norm of x to power 4 plus 2 times x1 square x2 square. Now, we simply take the first two term, we can take the norm of x square out, 1 minus norm of x square plus 2 times x1 square x square. So, now if we define a domain like this, that if norm of x is less than 1 and greater than 0, then it will take this value is positive, this value will also be positive because norm of x is less than 1 and this is also positive here. So, it means that in this range your V4x is all the time positive here, and if V4x is 0 implies what, that norm of x square minus norm of x to power 4 plus 2 times x1 square x2 square. So, here we can simply say that at 0 comma 0 it is taking value 0. So, 0 comma 0 is certainly the point where V4x is 0, and if we put this condition that norm of x is less than 1, then this is the only point where it is vanishing, because in that case when norm of x is less than 1, then this is positive, this is positive, this is positive. So, sum of the square will be positive. It means that this can be make 0, this will be positive if x1 square x2 square is 0 and this term is also 0. So, this is possible, this cannot be, okay. So, let me write it here. If norm of x is less than 1, then this will be 0 provided norm of x square into 1 minus norm of x square equal to 0, and here x1 square x2 square equal to 0 simultaneously. Now, this implies that x1 equal to 0 or x2 equal to 0 here, and this 0 implies this cannot be 0. So, this cannot be 0. So, only possibility is that norm of x square is equal to 0. So, this implies that x1 equal to 0 and x2 equal to 0 here. So, it means that if we restrict our domain as norm of x less than 1, then V4x will take the value 0 only at the origin and no other point. So, it means that V4x is a positive definite function in a domain norm of x less than 1, right, and it is greater than or equal to 0. So, in this, so in unit circle, so in the interior part of unit circle, it is a positive definite scalar function. Okay. So, here we have defined this. Now, in general, we can define the Lyapunov function as a quadratic form basically. So, we will now discuss some concept related to quadratic form. So, let v of x is given as summation I comma j equal to 1 to n bij xi xj. Here xi and xj are say component of x. So, here it is x1 to say xn here, right. So, with the help of x we can define Vx as this I comma j equal to 1 to n bij xi xj, where bij is equal to bji, and we call this as a quadratic form. So, now with the help of this quadratic form, let us find out the derivative here. We will see that how this calculation of derivative is quite important. So, that derivative of v with respect to 1 means x dash equal to f of x is defined as the scalar product v star x equal to grade of v of x dot f of x. So, grade of v of x will be double v by double x1, double v by double x2 and double v by double xn, and then f of x means your f of x is basically f1x, f2x and so on. So, when you take the vector product say dot product, then it is double v by double x1 into f1x plus double v by double x2 f2x plus so on double v by double xn fnx here. So, v star x we define as grade vx dot f of x here, and it is given by the expression given in 2. Now, if x equal to xt is any solution of 1 means x dash equal to f of x, then we can in fact use chain rule to obtain d by dt of v of xt. So, here it is given as any x1 to xn, it may not be the function of n here. So, it may not be a function of t here. So, now let us assume that x is a function of t, and now find out d by dt of v of xt. So, this can be done by choosing the while using the chain rule. So, here v is a function of x and x is a function of t. So, to find out d by dt of v of xt, so here it is v is a function of say x1 to say xn, and each one is a function of t here. So, we to find out dv by dt here, we simply say that derivative of v with respect to x1 and derivative of x1 with respect to t. So, double v by double x1 and dx1 by dt plus double v by double x2 dx2 by dt and so on. So, now if you look at here, if you look at the 1 here, so this I can write it as x1 dash equal to f1 x1 to xn, x2 dash equal to f2 x1 to xn and so on, xn dash equal to fn x1 to xn here. So, using the expression for x1 dash, I can write this as double v by double x1, in place of x1 dash we can write f1, and double v by double x2 in place of x2 dash we can write f2 and so on. So, if you look at this is nothing but double v by double x1 and this is f1 plus double v by double x2, it is f2 and so on, double v by double xn fn. So, if you look at this is nothing but the expression given in 2. So, we can write this as v star of x of t here. So, by d by dt vxt is nothing but v star xt. So, it means that this the derivative of v with respect to 1, which is given as v star x is given by d by dt of v of xt when x is a function of t here, right. Now, let us consider this system x1 dash equal to x2 and x2 dash equal to minus x1 minus 2 x2. Now, here we try to find out the V star here. So, V star here. So, first look at let us say that V x1 comma x2 is 1 upon 2 x1 is square plus x2 square, and we want to find out V star here. So, V star is basically what? V star is nothing but grade of V dot f of x, right, or we can say that it is nothing but d by dt of V of x of t here, right. So, we will use this thing. So, if we use this, then it is what? It is dou V by dou x1 and x1 dash plus dou V by dou x2 x2 dash. So, what is dou V by dou x1? So, if you look at here, we can find out dou V by dou x1 is nothing but simply x1. It is 2 times x1 and 1 by 2 is already there. So, we can simply say it is nothing but x1. So, it is x1 x1 dash plus similarly dou V by dou x2, it is 2 times x2, 2 is can be cancelled out from this. So, it is again x2 and x2 dash here. Now, we already know what is the expression for x1 dash and x2 dash. So, we can write x1 dash is x2 here plus x2 dash is minus x1 minus 2 of x2 here. So, if you simplify x1 x2 minus x2 x1 minus 2 of x2 square. So, this will be cancelled out and it is nothing but minus 2 of x2 square. So, V star is given as minus of 2 of x2 square here. So, here this V star is given as minus 2 of x2 square. We can easily check that this is nothing but negative semi definite function. Anyway, so now once we have something related to this function Vx, now let us consider the main theorems for finding the stability of given system. So, one important theorem is given as theorem number 3. So, it says that if there exists a scalar function V of y that is positive definite and for which V star y is less than or equal to 0 on some region omega which contains the origin, then the 0 solution of y dash equal to f of y is stable. So, here we are assuming that 0 is a solution of y dash equal to f of y, and we are able to find out a function V of y which is positive definite and V star y is negative semi definite. In that case, origin which is 0 solution is a stable solution. So, basically it is what we are able to find out a positive definite function whose derivative is negative semi definite. Then we are saying that y dash equal to f of y has a 0 solution which is a stable solution. Okay. So, since V is positive definite, then there exists a sphere of radius r greater than 0 centered at origin contained in omega and such that V of y is greater than 0, y not equal to 0 and norm of y is less than r equal to r, and V star y is less than or equal to 0, norm of y less than or equal to r. So, here the first expression is given with the help of positive definiteness of V of y. So, since V of y is positive definite, so it can take value 0 only at origin and in all other point it is taking the positive value and only. So, V of y is positive when y is not equal to 0 and norm of y is less than or equal to r. We are considering only everything in the inside the sphere of radius r greater than 0, and it is already given that V star y is less than or equal to 0 on some region omega containing the origin. So, this sphere is inside your omega. So, this also be true that V star y is less than or equal to 0, norm of y less than or equal to r here. Now, let us take one initial point, say y naught, which is non-zero and it is inside your omega, inside your sphere of radius r. So, it means that norm of y naught is less than r be given. Now, we find out one solution phi t of y dash equal to f of y with phi of 0 equal to y naught. So, let us consider a solution of initial value problem, that is y dash equal to f y with the condition that phi of 0 equal to y naught. So, we so here I am assuming that f is smooth enough. So, it means that we assume that that solution exists. So, by local existence this solution exists on some interval, say 0 t less than or equal to t1 for some t1 greater than 0. So, this is standard existence theorem, that if f is smooth enough, then this initial value problem has a solution. In fact, if we take more smoothness on f, then we can have a unique solution here, and this can be continued to the right of t1 as long as that norm of phi t is less than or equal to r. So, we keep on applying the same result, and we can say that the solution of y dash equal to f y with phi of 0 equal to y naught can be continued, can be extended till the right of your t1 also, as well as t1 also, only till your norm of phi t is less than or equal to. It means that phi t is inside the sphere of radius r. So, suppose that 0 to t1 is the largest interval of existence of the solution phi t. So, it means that by doing by repeated application of existence theorems, suppose this is the interval 0 to t1 is the interval where your solution exists. So, phi t that can be achieved by the continuation. Then claim is that either t1 is less than infinity, t1 is equal to infinity, or t1 is less than infinity. Now, we want to show that if norm of y naught is small, then and t1 is less than infinity, then we can get some contradiction. So, it means that for a small enough norm of y naught, the second case, that is t1 is less than infinity, is not possible. So, idea is to show that if we take a solution inside the sphere R, then it will remain all the time in the sphere of radius r only. So, it means that when t1 is tending to infinity, then also your solution will remain inside the sphere of radius r. So, it means that the possibility that t1 is less than infinity may not arise. So, t1 has to be equal to infinity. So, to show that this is true, we use this condition that v star phi t is less than or equal to 0, and we have already shown that v star phi t is nothing but d by dt of v of phi t here. So, through t less than or equal to t1 t greater than or equal to 0 less than t1, d by dt of v phi t is less than or equal to 0. This is already given that v star phi t is negative semi-infinite. So, we simply integrate with respect to t here. So, we will get v of phi t minus v of y 0 from 0 to t v star phi of s ds. Now, v star phi of s is less than or equal to 0, t is positive. So, this will be less than or equal to 0. So, it means that your v of phi t is less than or equal to v of y naught, which we have achieved from this. Now, we already know that since y naught is non-zero, then phi t cannot be 0. Why? Because if we have y dash equal to f of y, and initial condition is that your phi of 0 equal to y naught. Now, if y naught is non-zero, then if y naught is 0, then it will have only a unique solution, that is 0 solution. But if y naught is non-zero, then 0 solution cannot be a solution of this, and by existence and uniqueness theorem, if phi t is a solution of this initial value problem, then phi t cannot be equal to a 0 solution. So, it means that phi t is not a 0. So, it means that v of phi t has to be greater than 0 because v is positive definite. So, it means that with the condition that v star phi t is non-positive and v is a negative definite, we have obtained that 0 less than v phi t is less than or equal to v y naught for all t less than t1 here. So, that is the inequality given in equation number 4. So, where the inequality follow from the assumptions that y naught not equal to 0. So, this inequality is followed from the assumption that y naught is non-zero. So, it means that 0 is not a solution of this, and hence phi t is all the time positive non-zero. So, let epsilon greater than 0 be given with the 0 less than epsilon less than or equal to r, and let S is equal to all those y such that norm of y is less than or equal to r and greater than or equal to epsilon. Now, what we try to prove now, that if this 4 is true, then your solution will remain very small if we take y naught, norm of y naught very small. So, that is what we want to show, that we want to find out for every epsilon they exist greater than 0, they exist a delta greater than 0 such that norm of this phi of t is less than epsilon whenever norm of y naught is less than delta. So, we want to show this thing. So, let us say that corresponding to this epsilon you define a domain like S. So, let S equal to all those y whose norm is lying between epsilon and r, right, and we assume that then by continuity of V and the fact that S is closed, this is a closed sphere, basically a closed annulus, basically it is this, it is like this. So, it is epsilon and it is r. So, this is the reason which is given by this S, right. So, it means that S is closed because it contains the boundary points also. So, S is closed and V is continuous. So, we can use the Heisenberg theorem and we can say that continuous function defined on a closed region will attain the maximum and minimum value inside your closed region here. So, let us say that mu, which we define as the minimum of V of y, where y is running over this S. So, it means that mu exists and it is strictly positive. Why so? Why? Because norm of y is greater than or equal to epsilon and epsilon is positive, right, and so it means that Vy take only a positive value in this region S, right, and it will not take any negative value. So, here we simply say that Vy is strictly positive. It can take only value 0 when your y is 0. Okay. So, since limit y tending to 0 V of y is equal to 0, we can choose a number delta which is less than this mu such that norm of y naught is less than or equal to delta here, and V of y naught is less than mu here. So, it means that we are choosing norm of y naught less than delta and delta is less than mu. So, it means that this norm of y naught is less than mu here. Okay. So, we simply say that V of y naught is less than mu here. So, here since limit of y tending to 0 V of y is equal to 0. So, we can find out a number delta which is positive such that norm of y is less than or equal to delta and V of y naught is less than the mu which we have defined as minimum of V of y here. Then according to 4 the solution phi t with the condition that phi of 0 equal to y naught and norm of y naught is less than or equal to delta, it satisfies the following inequality that V of phi t is greater than 0 and it is less than or equal to V of y naught and V of y naught is less than mu here. So, here we assume that norm of y naught is less than or equal to delta, where y naught is nothing but phi of 0. So, this is true for t less than t1 here, but we already know that what is mu here. Mu is the minimum of V of y, y belongs to S, then this implies that norm of phi t has to be less than epsilon for t between 0 to t1 here. Why so? Because this implies that t1 equal to plus infinity. First of all, since V of phi t is less than mu, you can look at here, then your phi t cannot be the element of S here, and S is this annulus region. So, it means that your phi t is somewhere outside this annulus. So, either it will be here or it will be here. Now, since phi t is tending to 0, then this V of phi t is tending to 0. So, it must be in a region which contain the origin. So, it must be here. So, it means that if phi t is here, so it means that norm of phi t must be less than epsilon for t less than between t lying between 0 and t1 here. So, and this also implies that t1 is equal to infinity because if it is not, then we can find out a some time t2 greater than equal to t naught with the condition that phi of t2 equal to epsilon. Then for t equal to t2, we also have from the definition of mu, we can say that since phi of t2 is equal to epsilon, so it means that v of phi t2, and since mu is a minimum of all those mu is a minimum of values of Vy over S, and phi t2 is belonging to S. So, it means that V of phi t2 is greater than equal to mu, and V of phi t2 by 4, it is less than or equal to V of y naught, and V of y naught is less than mu. So, it means that this condition cannot hold true. So, it means that we cannot have any point t2 where phi norm of phi t2 is equal to epsilon. So, it means that norm of phi t2 is less than epsilon, and this t1 is all the time plus infinity, right. So, it means that thus t1 is equal to plus infinity, and corresponding to the given epsilon greater than 0, we have found a delta greater than 0 such that norm of y naught is less than delta, implies that norm of phi t is less than epsilon for 0 lying between t is less than infinity, and hence the stability of the solution phi t is proved here. So, solution here, the stability of 0 solution is proved here. So, it means that if given a system x dash equal to f of x, where f is smooth enough, then a 0 solution of this, it means that x t identically equal to 0. Here we are assuming that f of 0 equal to 0. So, 0 solution of this system is stable provided that they exist a scalar continuous function v of x which is positive definite. So, v of x is positive definite and v star x is negative semi definite here. So, here if you look at the expression of v of x is we have not said that it is somewhere related to x dash equal to f of x. So, here our how to find out v of x is up to us, such that the v star x, it is the derivative of v x along the system x dash equal to f of x is satisfying this condition that it is negative semi definite, then your 0 solution is stable solution. So, if you look at this theorem, then here the important part is to construct this function v of x, and here if you look at, we have not obtained the solution of x dash equal to f of x. What we require is in finding the v star x, the expression of f of x which is already given here. So, without finding the solution of this dynamical system, we are able to predict the stability of 0 solution here, and hence sometimes we call this method as Lyapunov Dirac method for finding the stability of the 0 solution. So, with this we conclude our this lecture, and we will continue discussing some more result based on the Lyapunov function. So, in next lecture we will discuss some more properties telling about the asymptotically stability of 0 solution and instability of 0 solution, in fact equilibrium solutions, and how to construct Lyapunov function in some important cases here. So, with this we end here, and thank you very much for listening. Thank you.